We're more than halfway through this course on the 12 essential scientific concepts, and we've already attempted to answer many profound questions, like what is life? How did the diversity on Earth come to be? What is energy? We've also considered how science has led to inventions that have completely changed our world: electricity, engines, and airplanes. But there is one question that we haven't touched upon yet, and one that is arguably the granddaddy of them all. How did it all begin? An age-old question, and one that has intrigued humans since the beginnings of civilization. Virtually every culture has tried to answer this question one way or another, and the collection of origin stories that we've come up with over time is nearly as diverse as our species. Although it accounts for most, if not all, of the available evidence collected thus far, the Big Bang theory of the origin of the universe is certainly not among the least bizarre. The idea that everything started from a single point and that our universe continues to expand is baffling. And yet, there's a beautiful elegance to the theory that has captured the imaginations of our era's greatest thinkers. In this lecture, we're going to travel back to the very start of time and navigate the murky beginnings of everything. We'll evaluate the theory by considering the evidence, and we'll ponder the mind-boggling implications that must follow if the theory is indeed fact. As we talk about the Big Bang and theories of quantum physics, we need to revisit what scientists mean by theorizing. The ancient Greeks, among their many contributions, invented the word theory to mean to look at or contemplate. But it's constructed from the words I see, orao, and the divine, theon. Understanding the universe was a sacred process, leading to the ultimate truth. In scientific parlance, a theory is more than just speculation. When we want to speculate, we use hypotheses. But when these hypotheses are tested and evidence accumulates supporting a subset of them and falsifying others, we have the beginnings of a theory. And a theory, then, is an explanation of some phenomenon in the natural world that has been repeatedly tested, confirmed, and substantiated through objective observation, converging evidence, and carefully designed experimentation. For scientists, a simple, elegant theory that accounts for all of the available evidence is indeed divine, and the Big Bang theory is one such example. Through the course of human evolution, we've developed one adaptation to our environment that's been particularly useful. When we see two things happening at the same time, we infer that one of them caused the other. Sometimes we're wrong, and they just happen to occur at the same time. But often, our inference helps us predict the future. If we encounter the cause again, we'll know what the effect might be. This line of reasoning is so powerful that it's almost impossible for us to conceive of something happening without an underlying cause. This cognitive or brain bias of ours is at the very crux of the difficulty we have in understanding how the universe came to be. We need there to be a cause. We're all somewhat familiar with the main concept behind the Big Bang theory. All of the universe began with a bang, an explosion of matter that created all we know. But this view of the Big Bang is actually incorrect in many ways. For one thing, nothing actually banged. For another, matter didn't even exist when it happened, and even today seems to be only a minuscule portion of what the Big Bang produced. And one more. The Big Bang theory actually explains what happened just after time began and the universe was an infinitesimal speck of energy. Have I blown your mind yet? Hopefully not, because there's lots more to come. But let's get back to that first big revelation. The Big Bang was not an explosion. Nothing blew up. Instead, the teeny tiny speck of the beginning of the universe began its colossal expansion 13.7 billion years ago in an instant. So, Why do they call it the Big Bang then, you might ask? Well, it turns out that the name was coined by a physicist named Fred Hoyle on a radio show that the BBC aired. Now, Hoyle was a proponent of a rival theory of the universe, the steady-state theory. Some argue that he coined the phrase to be pejorative and imply the ridiculousness of the idea, but he insists it was simply the best description he could think of. Fred Hoyle was such an interesting character that his story deserves a slight diversion. Hoyle was an English cosmologist and a writer of science fiction. At the peak of his career, he was an astronomy professor at Cambridge, but he resigned from his academic career in 1973 to write immensely popular science books. His greatest contribution to cosmology came in 1957 when he, along with an American physicist named Willie Fowler, wrote a paper demonstrating that all of the elements that make up our world come from the stars. Ages ago, hydrogen fueled the creation of all other elements which were distributed across the universe when stars exploded. These elements then later combined to form the planets, the oceans, the mountains, and eventually, us. Everything we know is in fact stardust. But despite this paradigm-shifting discovery, Hoyle didn't make many friends among fellow scientists. He was rude, derisive, cantankerous, and worst of all, many of his ideas later in life resembled the ramblings of a lunatic. He thought that the flu was caused by extraterrestrial microbes falling to Earth, and that the fossils in the British Museum that show the link between dinosaurs and birds were faked. But perhaps his biggest misstep, though one whose sentiment I admire, was in questioning the Nobel Prize Committee in 1974. That year, the prize for physics was awarded to a man by the name of Anthony Hewish for his discovery of pulsars. And when asked about the prize by a reporter, Hoyle quipped that Jocelyn Bell was the actual discoverer, not Hewish, who was her supervisor, so she should have been included. That's every graduate student's nightmare. He immediately apologized and justified his remarks in an editorial, but the damage had been done. And so, in 1983, when Willie Fowler got the call that every scientist dreams of getting from the soft-spoken Swedish Nobel Prize Committee member, he was shocked to discover that the prize would be awarded to him and one other for their contribution to the research uncovering our stellar origins, with the blatant omission of Fred Hoyle from the list of winners. And of course, Hoyle was also a vocal opponent of the Big Bang theory. But his derision of the theory was in fact absolutely true to the spirit of science. Science can only progress if theories and hypotheses are rigorously tested, preferably by those who seek to prove them wrong. The most vehement believer, after all, is the converted skeptic. And so, despite the name, the first big idea is that the Big Bang was not an explosion, but rather an expansion. From a tiny, dense point, all of space and time, for that matter, extended outwards, initially at a very fast pace, and eventually slowing down. The second big idea is that at the beginning of the Big Bang there was no matter. The speck that eventually became everything in our universe was infinitely dense and extremely hot. As the universe expanded, it lost density and heat, and eventually matter began to form, and through radiation, it began to lose energy. One effect of the Big Bang is that the four forces of nature that are the topic of our next lecture were created. But at the beginning of the Big Bang, they were arguably one unified force. How they work together remains one of the big mysteries of astrophysics. The third idea to keep in mind is what the theory describes. What happened after the expansion began? Not only all space, but also all time began with the expansion. What could have come before, if there was a before, is still in the realm of speculation. Given these basic ideas, let's turn now to the evidence that supports the Big Bang theory. Believe it or not, it's all around us. How do we evaluate a theory that provides an explanation for something that may or may not have happened 13.7 billion years ago? To put that number in perspective, the entire history of human civilization covers about 10,000 years. If we imagine that the lifetime of the universe is mapped onto 1 year, we can get a sense of where our place is along this timescale. Our brains are notoriously bad at understanding large numbers, so this kind of analogy can be really helpful. In this cosmic calendar, as it's called, and which Carl Sagan first popularized, the Big Bang happens at midnight, leading into January 1st. And then, it's not until the 11th of May that our Milky Way galaxy is finally formed, about 5 billion years after the Big Bang. The Sun is formed around September 1st, and life on Earth emerges on September 21st, or 3.8 billion years ago. By December 5th, or about 1 billion years ago, life goes multicellular. That's just the last month of the year. Now, just as the holiday season is busy for all of us, things pick up pretty quickly at the end of December. We're talking now about only the most recent 500 million years of the lifetime of the universe. But this is where all the action that's really relevant to us is happening. On December 22nd, amphibians emerge, with reptiles coming on the 23rd, then mammals evolving finally on Boxing Day, or December 26th. Birds follow on the 27th, and flowers brighten things up on December 28th. Then on the 30th, there's a catastrophe. A massive comet or asteroid hits the Earth, and over the course of the next 66 million years, all non-avian dinosaurs go extinct. Still on December 30th, the first primates emerge, and it's not until 10:24 p.m. that primitive humans walk the Earth. Modern humans, anatomically speaking, come at around 11:52 p.m., and we sort out agriculture at 11:59 p.m. and 32 seconds. Christopher Columbus reaches the Americas at 11:59 p.m. and 58 seconds, 2 seconds before the turn of the calendar. But the point of this demonstration is to put the Big Bang in context. To evaluate the theory, we need to delve into two fields of physics: astronomy, or the observations of stars and celestial bodies, and cosmology, or the study of the astrophysical properties of the universe, such as what the stars are made of. Let's start with the fundamental idea that the universe expanded from a single point and continues to expand today. The origin of this idea is attributed to a Belgian Catholic priest named Georges Lemaitre in the 1920s, who first devised a model of an expanding universe and proposed that the expansion would have an effect on the wavelength of electromagnetic energy traveling through space. Specifically, he predicted that light emitted from distant stars and galaxies would look more reddish to us than those that are closer. As stars and other galaxies move further away from us, there's a shift in the signature of hydrogen as measured by spectroscopy. The light coming from the faraway hydrogen atoms is shifted further down the wavelength spectrum. It's called the redshift, and it's evidence that galaxies are receding away from us. This redshift effect is also called the relativistic Doppler effect, a version of which we briefly encountered in Lecture 8. Think of a siren coming from an ambulance. Coming towards us, it sounds high because the frequency of the sound wave that we perceive is higher. In the instant that it passes us, we hear it at the same frequency as it's emitted, and as it drives away, the siren sounds lower, as the frequency of the sound wave decreases. As galaxies recede from us, just like the ambulance siren, the frequency of the wavelength of light that we observe decreases and becomes more red, hence the redshift. US astronomer Edwin Hubble had already published his observation that the starlight from more distant galaxies reddens more than closer ones, and these observations were confirmed in 1929. So Lemaitre extrapolated from this information that if the universe is expanding today, it must have started at some point in the distant past with a size of 0, or very, very small. Lemaitre called this hypothesis the primeval atom, and while he was eventually proved right, even Albert Einstein found his notion a bit ridiculous. "Your calculations are correct," he said, to Lemaitre, but your physics is abominable. By the 1930s, though, Einstein was a convert, commenting that, and I quote, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened," after hearing Lemaitre speak in California. So the first evidence supporting the Big Bang theory came in the form of the reddening of light that comes from distant galaxies. The next major point came from George Gamow, a Russian theoretical physicist notorious for his bacchanalian lifestyle, which likely eventually caused the liver disease that killed him at age 64. Fond of pranks, Gamow included one in his seminal paper on Big Bang nucleosynthesis, which explains how the current levels of hydrogen and helium in the universe were created by reactions during the Big Bang. He added an extra author just for the fun of it. The paper was published in 1948 with authors listed as Alpha, Beta, and Gamma, a pun on the first three letters of the Greek alphabet, Alpha, Beta, Gamma. Beta had not been consulted and had nothing to do with the work. But the point of the paper was that the idea that if the early universe was hot enough, it would act as a pressure cooker. At these high temperatures, basic particles like electrons, protons, and neutrons would be moving around too quickly to combine with each other. But as the universe expands and the space cools, the neutrons and protons could come together to form nuclei of elements. This idea was particularly useful in describing the formation of the lightest elements, hydrogen and helium, and provided an account for their abundance in our universe. Our universe is around 74% hydrogen and 25% helium, with all the other elements put together representing a tiny percentage of matter. The Alpha, Beta, Gamma paper predicted precisely this state of affairs. The calculations that Alpha conducted didn't work so well for the heavier elements, however. And Fred Hoyle set out to disprove the Big Bang theory by explaining their formation in the stars in his famous 1957 paper. But Alpha and Gamow also realized that the Big Bang would leave another signature, a thermal radiation that should be found in trace amounts everywhere in the universe. And in fact, cosmic microwave background radiation, or relic radiation, has been discovered in distributions that fit that description. The Big Bang is still considered the best explanation for this relic radiation pattern and its fluctuations. The third test of the Big Bang theory came in the form of the shape of the contents of the universe. The Big Bang theory makes certain predictions with respect to how galaxies and quasars are distributed in space and how they're shaped. For example, in the first few moments after the Big Bang, the theory predicts that there was a period of rapid expansion or inflation. This inflation would have been enabled in part by the fact that the universe at that point would have been made up of an unstable form of energy that we still don't understand. This energy would cause the matter in the universe, galaxies, and so on, to be unevenly dispersed. In fact, the very sort of pattern that the theory predicts is visible in photos that NASA quaintly calls baby pictures of the universe, snapshots taken by a satellite of background radiation from about 400,000 years after the Big Bang. Yet another source of evidence comes from quasars and other galaxies. Quasars are the most distant visible objects. They are massive black holes surrounded by a flat, disc-shaped gas called an accretion disk. They're extremely bright, but they look red to us because they're so far away and are receding from us. The first quasars and galaxies were formed about 1 billion years after the Big Bang, and we can observe them in different stages of their evolution. Because light from faraway galaxies must travel all the way to Earth to be observed, what we see of them today represents what they were a long time ago. The further the galaxy, the older the snapshot that we glimpse. So we can compare observations from near galaxies with those from distant ones and get a sense of how galaxies evolved over time. These observations agree with simulations that are generated by models of the Big Bang. They also refute the predictions of the biggest rival to the Big Bang model, which is the steady state model championed by Fred Hoyle and others. The steady state theory posits that matter is eternal and that no new matter is created as the universe expands. There is no need for a beginning and an end in this theory. But given the accumulation of evidence in favor of the Big Bang, this theory is now considered obsolete. It seems that there was a finite beginning, and there probably will eventually be an end. But the end of the universe is a long way away, and in 2011, more evidence for the Big Bang was discovered in very distant quasars. But by analyzing the absorption lines of the spectra of these quasars, astronomers found clouds of primordial gas. Unlike all other gas clouds observed, these clouds contained only 2 elements, and no trace of the heavy elements made by the stars. There was only hydrogen and deuterium, also known as heavy hydrogen because it's an isotope of hydrogen. These observations prove that at some point during the life of the universe, matter consisted almost exclusively of hydrogen, a prediction stemming from the Big Bang. And there are still other lines of evidence supporting the theory, primarily related to the age of the universe and its contents. The veracity and explanatory power of the Big Bang theory is great. And so, if we take it for granted that the theory is correct, what are its implications? Where do we go from here? Well, unfortunately, there are 3 main options, and none of them are desirable. There's the Big Crunch, the Big Freeze, and the Big Rip. Apparently, astronomers could use a little help in the literature department. To understand the rationale behind the first 2 models, we need to add one more concept to our arsenal, the critical density. The critical density of the universe is the value at which the universe is in balance and expansion stops. We can compare the actual density with this critical value and get a ratio. If the answer is more than 1, then the universe is collapsing and its shape is becoming more like a shrinking sphere. If the answer is less than 1, then the critical density hasn't been reached yet and the universe is still expanding with a hyperbolic shape and negative curvature. If the ratio is exactly 1, then the universe is flat with no curvature. And today, the universe remains very close to being flat. What would happen then if the mass density continues to increase? Well, eventually the universe would max out in terms of size and begin to collapse onto itself. It would become more dense and hot once again, and the Big Bang would happen in reverse. Now we have the Big Crunch. What would happen if the universe didn't reach the critical mass density? Well, it would continue to expand and cool. Stars would burn out, leaving their black holes in their wake. These large masses of matter would eventually collide and form even larger black holes, and the temperature of the universe would reach absolute 0. The Big Freeze. But what neither of these 2 scenarios take into account is dark energy, a hypothetical form of energy that accelerates the expansion of the universe. Indeed, based on our observations, the universe is expanding at an accelerated rate. And so scientists have proposed that dark energy exists to explain this phenomenon. There is no direct evidence for dark energy, but it does seem to provide the missing link in explanations of other observations of the cosmos. We don't know much about dark energy. It could be some kind of new form of fluid, or it could be some new property of the vacuum of empty space, or some other physical phenomenon that we have yet to discover. One thing we do know is how much of it there is. It seems very odd that we can quantify it in a way without really knowing what it is that we're measuring. Anywhere from 68 to 74% of the universe is dark energy. There are so many things about space that we don't understand, and by some accounts, dark energy is the biggest mystery of them all. So, if we take the existence of dark energy and add it to the Big Bang model, the implications are that the universe will continue to expand at an accelerated rate. More and more of it will pass out of our reach. What will happen then? The honest truth is, of course, that no one knows. There's still room for a satisfying theory. In 2003, the Big Rip was proposed, a hypothesis that predicts that the matter of the universe, stars, galaxies, all atoms will be torn apart by the expansion of the universe at a specific time in the future. At some finite point in time, the expansion will become infinite. But everything we think we know about dark energy might turn out to be false once we can finally make some direct observations. At that time, all bets are off as to how these predictions will actually pan out. In the meantime, we're stuck with the tools that we've built ourselves to learn more about the universe. Observations of celestial bodies and astrophysics can only take us so far in our ability to evaluate the Big Bang theory. To get more answers, we need to simulate the conditions of the universe around the time of the Big Bang in order to make direct observations of what happens under those circumstances. To that end, massive efforts have been undertaken in the last decade or so to recreate the Big Bang, albeit on a much smaller scale. These efforts have resulted in the construction of particle accelerators, such as the Large Hadron Collider at the European Organization for Nuclear Research, or CERN, near Geneva in Switzerland. The Large Hadron Collider, or the LHC, is the world's most powerful particle accelerator, made up of a 27-kilometer ring of superconducting magnets with accelerating machines boosting the energy in the ring along the way. Inside the accelerator, two high-energy particle beams are sped up until they almost reach the speed of light, and then they crash into each other. At these speeds, the reaction creates temperatures 1,000,000 times hotter than the center of the sun, mimicking the conditions of the universe in the first billionth of a second after the Big Bang. With this accelerator, scientists are discovering what holds atoms together and gives them their mass, including the action of the elusive Higgs boson, which seems to hold the key to our understanding of exactly how the remnants of the Big Bang turned into stars, planets, and eventually, all of us. This amazing journey from the beginning of the life of the universe to its current state today teaches us about ourselves and our place within it. For some people, the discovery that our entire human past is only a few hours in the cosmic calendar feels overwhelming. Does this mean that our short little lives hold no meaning? I would argue that it certainly does not. In fact, it gives us a sense of how far we've come and how connected we are even to the very beginnings of the universe. And surely life gains meaning through the connections that we make to each other and to our world. Part of the seduction of studying the origins of the universe, dark energy, and the other features of space is the quest for meaning, the holy grail of mysteries. Why are we here? Where did we come from? And how can we make the best use of our time on Earth? With each step forward in our search, every answer reformulates the fundamental question: what is the meaning of life? Why us? Why now? And what is to come tomorrow? We started this course by learning how science defines life and how the chemistry and biology of organisms enable us to be alive. With the Big Bang, we can begin to grasp how matter might have come about. And in the next lecture, we'll explore the forces of nature that define the world as we know it and demonstrate why matter behaves the way that it does. Through an understanding of the forces of nature, we'll unravel further mysterious aspects of our universe.